Section 8.5, estimating a mean. Just like confidence intervals for proportions, we have conditions that need to be met before we create an interval for a population mean. For proportions, it's the random sample condition along with the success fail n times p and n times q condition. We don't have a p or a q for these types of problems, so instead we're going to use the nearly normal / large counts condition. Either the data comes from a population that's approximately normally distributed, or we have a large enough sample for the central limit theorem to apply. For example, how much do people spend on engagement rings on average? To find out, the New York Times and Morning Consult surveyed a random sample of 1,640 US adults who have been engaged, checked to see if the conditions for calculating a confidence interval for mu are met. So in these next two sections, we're talking about confidence intervals for means, which is different than the last two, which were calculating confidence intervals for proportions. So our underlying question here is quantitative. How much do you spend on an engagement ring? And we get numerical answers. In the past two sections, we were dealing with questions that were categorical, such as what proportion of US adults have been engaged. So for the conditions, we need a random sample, which is what we have because it's stated right here in the problem. Those 1,640 US adults are less than 10% of all US adults. And different from the last section where we checked NP and NQ, this time we need to either have a population that's normally distributed. It doesn't say anything about that in the text of the problem. However, this sample size is large enough because it's bigger than 30, where the central limit theorem will apply and our sampling distribution will be approximately normal. As for the equation that we'll be using, let's first recap on what we learned in the last section. So a confidence interval for a population proportion started with our point estimate, p hat. That's the statistic that we get from our sample. And then we're going to add and subtract to that the margin of error, a z-score times radical pq over n. Now this standard error here we can't do because we don't have a p and a q. So that's going to change a little bit, but we're still going to have our critical value out front and then a standard error, which will change because we're dealing with means instead of proportions. Now here's what's changing when we create a confidence interval for a mean. Instead of starting with p hat, we're going to start with x bar, which is our point estimate. It's the result of our sample. How much on average did the 1,640 people spend on an engagement ring? We have our critical value, or critical z-score in this case, which actually is going to change in just a minute, but for now we'll leave it as it is, times the standard error. So the standard error had been radical pq over n, but we don't have a p or a q for this problem, so we use this familiar equation from chapter 7, sigma over radical n. This follows the same form, the statistic plus minus the critical value times the standard error of the statistic. Now, the issue that we're going to run into is because we don't know what mu is. Remember, we're creating a confidence interval to estimate mu from a sample statistic. And because we don't know what the true population mean is, we probably don't know what the true population standard deviation is. That's what sigma is there in that equation. So instead of using sigma over radical n, we're going to use S sub x, okay, which is the standard deviation from the sample. Okay, so this is a sample statistic in the same way that x bar is a sample statistic, meaning that every time we take a sample, these two things are going to change. So there's an added level of variability in this confidence interval, and that's going to change how this critical value works. So for these problems, we're introduced to a new distribution. We're no longer using the normal distribution, the z distribution, and instead we're using something called the t distribution. We can see in our equation here that z-score is replaced by t-score, but we're still following that same form of statistic, which is our point estimate from the sample, plus minus our critical value, t star, times the standard error of the statistic. The whole reason that we need to use t star instead of z star is because we don't know what sigma is. We don't know the standard deviation of the entire population. We only know the standard deviation of our sample. S sub x. And using that sample result instead of the population parameter introduces an added level of variability, which is accounted for when we use that t critical value instead of z. How do we find a critical t-score? Well, instead of using that yellow z-score table, we're going to use our green t-score table. Across the top, you're going to see a number of different confidence levels. We're going to look for the one that's used in our problem, such as 95%. And then on the left, you'll see a column that says DF, which means degrees of freedom. This is determined by one less than the sample size. So for example, if we had a sample of size 10, we'd be on the line for 9 degrees of freedom. We find a 95% confidence interval, and then we just intersect those two values to find our critical t-score. If we have a degrees of freedom that isn't listed on the table, we use the biggest degrees of freedom that's still less than the correct one. So for example, let's say we were looking for one that said we needed degrees of freedom of 504 or 500 and let's say 96. We would use 500 instead of 600 because 500 is the biggest thing that we have that's still smaller than our actual degrees of freedom. Here's an example that uses a table that looks a little different than ours, but it's still the same idea. We want a 99% confidence interval. We have a sample size of 4, resulting in 3 degrees of freedom. So we're on this line right here. And we're going to intersect those two columns and find our critical t-score. So that would go right in front of our standard error where that critical z-score had been. And note that if we had used the critical z-score for 99%, we would have gotten a z-score of 2.576. So 2.576 times that standard error, but instead of using that z-score, we're using the much larger t-score. Okay, t-scores are a lot larger for smaller sample sizes, which means we're moving out more standard errors when we calculate our margin of error. If you look at the bottom of either this table on the screen or the one that I printed out for you, you're going to see a row that has the z-scores for each of those confidence levels. And that's because as the sample size increases and the degrees of freedom increases, our t-distribution looks more and more like a normal distribution. As noted before, if we're looking for a degrees of freedom that isn't on the table, we're going to use the closest one that's still below the actual degrees of freedom. We're not rounding up for our degrees of freedom. If we do that, we end up with an interval that's too narrow. And if it's too narrow, it won't be wide enough to capture that true population value as much as we're stating it is with, for example, a 99% confidence level. So try to answer these two questions using your table, your printed table, before I go over it using the ones on the display screen. We want a 95% confidence interval based on a sample of size 12, and then a 90% interval for a random sample of 48 observations. So for part A, the first thing we'd want to do is find the degrees of freedom. It's 1 less than the sample size, so we're going to be on 11 degrees of freedom. We take a look at our table, and we're going to intersect that 11 with a 95% confidence level. Those intersect, and we get a critical t-score of 2.201. For part B, we want a 90% interval with a sample size of 48, meaning we have 47 degrees of freedom, and that value is not in our table. And even though 47 is closer to 50, we're not going to round it up, and instead we're going to use the closest value that's still below that actual degrees of freedom. We intersect that with a 90% confidence level, and you get a critical t-score of 1.684. When it comes to the standard error, it's changing from the one we used in those proportions, p hat q hat over n, which we can't use because we don't have a p hat. And instead, we're calculating the standard error of our sampling distribution with the equation S over radical n. S is the standard deviation of the sample, and we need to use that because we don't know the standard deviation of the entire population, which is sigma. So with that said, here's the equation for our confidence interval for a mean. We have our statistic, our point estimate, the average from the sample. We're using a critical t-score instead of a critical z-score. And our standard error is S over radical n. So let's use that equation to calculate the confidence interval for the problem that we encountered earlier. We talked to 1,640 people about how much they spent on an engagement ring, and we found that they spent an average of $3,329 and a standard deviation of $4,739. These are sample statistics, meaning that they will change each time we take a sample. And we want to use those sample statistics to create a 99% confidence interval for mu, which is the true average amount that all adults spend on engagement rings. We'll start by finding the degrees of freedom, which is one less than the sample size, 1639. When we look for that on the table, we see that there is no 1639, so we'll go to the closest thing while still staying under that value and go to the row that has 1,000 for the degrees of freedom. That gives us a critical t-score of 2.581. We can plug everything into our equation. Our sample mean, 3329, plus minus that critical t-score, times that standard deviation from the sample, divided by the square root of that sample size. This is our margin of error, and if we calculate that out, we get 302. And to finish the calculations, we're going to add and subtract that value from X bar. We get an interval of $3,027 to $3,631. And as a final step, we're going to interpret our interval. We are 99% confident that the true mean amount that all U.S. adults spend on engagement rings lies between $3,027 and $3,631. According to tradition, you should spend 3 months of your salary on an engagement ring, and for U.S. adults, 3 months' salary is typically just above $15,000. Based on our interval, does this tradition still appear to be popular? Well, our interval is all very much below $15,000. $15,000 is not in this interval. It's way above it. And our interval is telling us what the plausible values that we believe the true mean could equal. We think it's somewhere between $3,027 and $3,631. These are all much less than $15,000. So this would be convincing evidence that this tradition is no longer popular.